last session of the day. Our first speaker, invited speaker, is James Quach from Melbourne. He actually was a postdoc here a few years ago. I just learned. Welcome you back. And he's going to tell us how to use somehow quantum batteries to replace classical electronics somehow. Let's see. Yeah. Please, floor is yours.
Yeah, thanks for that. Yeah, so I'm James Quach. I'm from the CSIRO, which is Australia's National Science Agency, based in Melbourne. That's the South Australia. Yeah, and so I was actually a postdoc here 8 years ago now, and I haven't been back since. And yeah, it brings back a lot of memory. It's a great institution here, so I'm really happy to be here. I was happy to be at my first QEI, and I really appreciate the introduction or the sort of background to QEI, because we also founded a similar conference. It's called the ICQE, International Conference on Quantum Energy. Slightly different focus. There we are looking at how quantum tech could be used to, quantum tech and science, could be used to solve future energy problems. So I think these two conferences are good complementary conferences. Well, anyway, today I'm going to be talking about our latest research, which is to look at how we can develop a new quantum computing architecture, which we believe is more scalable and also more energy efficient. And the way that we do this is to use quantum batteries to power quantum computation. So this will be the outline of the talk. I'll begin by talking about something known as the I/O bottleneck. And then I'll move to explaining our new quantum computing architecture powered by quantum batteries. I'll start using this cursor now, actually. There we are. Okay, and then we'll move to looking at how this new architecture can be truly used as a quantum computation by showing that it can be a platform for a universal gate set for quantum computation. And then using that gate set, I'll show how it can be used to implement a number of examples of some quantum circuits. Following that, look at the energy efficiency of this new architecture. And then finally, I'll talk about some of the open questions and challenges that still needs to be solved. All right, so quantum computing, it's meant to be a really powerful solution, but we don't have one yet. And the reason we don't have one yet is that it's quite easy to build a few qubits, but extremely difficult to scale it up. And to understand why, all you need to do is open up one of your quantum computers by your Googles and IBMs, because what you immediately see are all these cables. In fact, there are about 2.5 cables per qubit. And this poses some really big problems. First of all, they take up a lot of space. So you imagine if you want 1 million qubits, you're going to need 2.5 million of these cables, right? So it's not really feasible. Secondly, and perhaps even more important, is that these cables consume a hell of a lot of energy. So you need to cool them down, for example, from room temperature all the way to millikelvins, and that's going to consume a lot of energy. They also produce something known as a crosstalk, where the wires or the cables interfere with each other. And also these cables need to be synchronized to extremely high precision, to picosecond precision. So this together is known as the I/O bottleneck. So what we propose to do to solve this problem is to remove these cables and replace them with an internal quantum battery. So up here is a schematic of a 4-qubit system. And each of these qubits here is powered by its own drive line. So this is a conventional 4-qubit architecture. Down here, what we want to do, okay, that was working well for all, but okay, this cursor, all right. What we want to do is replace these drive lines with an internal quantum battery, which is then used to power the computation. So I have an animation which sort of visually depicts this. So what we first need to do is to power up the quantum battery. And once we do that, we can use this as energy source to drive the qubits to do its computation. And the beauty about this system is that once the qubit does its computation, it can send the energy back to the quantum battery without losing any energy. So it's a reversible process. And it can do this thousands of times a second. So the Hamiltonian that describes this system is your Tavis-Cummings Hamiltonian. Here you have a term which captures energy of the battery. Here, this term captures the energy of the qubits. And I pointed out here this omega because this is our controlling parameter, which is used to detune the qubit from the quantum battery, which is a resonator. And by doing this detuning, you can effectively do the quantum computation that you want to do. And I'll show how that's done in the next few slides. And finally, the third term there is the interaction between the battery and the qubit. So this is the Hamiltonian that we'll be using. Okay, so I'm going to show right off the bat some of the really cool things about this architecture. So one of the first things that we found was that the time it takes to flip a qubit or qubits from its 0 to 1 state scales super extensively. So this is really a really cool feature and really counterintuitive because with normal quantum computers, the time it takes to flip the 0 to 1 chip is constant and it's independent of the number of qubits that you have. But with this architecture, the time it takes to flip it decreases as you have more qubits. And for those who work in quantum computing space, this looks really, really familiar because this is one of the properties of quantum batteries. Okay, so also I'll point out. For this dot here goes from the light color to the dark color is the number of photons per qubit. So the more photons you have per qubit, again, the time that it takes to flip the qubits from the 0 to 1 state decreases. On the right-hand side here is a plot of the error when you flip it from the 0 to the 1 state. And again, what you find is something which is, again, very counterintuitive because the more qubits you have, the less error you produce. Because in normal architectures, the more qubits you have, the more errors are introduced. In fact, sometimes this grows exponentially, but in our system, the opposite occurs. So here, we prepared the battery in 2 states, one in the Fox state and one in the Kieran state. In both states, the error falls, this cursor falls as you increase the number of qubits. But for the Fox state works a little bit better. And on the horizontal axis, this is the number. This is not so great, this cursor. You know, I will. Oh yeah, did it work? No. You know what? It works good for a while, right? And then it gets complacent. Hey? Turn it around. Maybe the battery's flat or something, but it's gone. Oh, there it is. Okay, it's back again. Now, I'm going to persist for this a little while because it is recorded, so in case anyone watches it. Okay, so I was saying that the Fox state works a little bit better, and then I was saying that this horizontal, I've got to do this. This horizontal axis here is the number of photons per qubit. And as you increase the number of photons per qubit, the error again decreases. So these are really cool properties of the architecture. All right. Okay, so this calculation was done by preparing the qubit either in a Fock state or coherent state, and then having the qubits tuned to the resonance of the battery, and then allowing the system to evolve, and then working out the time at which it hits the one state. Now I want to go to explain to you how our architecture produces or can produce a universal gate set for quantum computation. So to show that a system has a universal gate set for quantum computation, you really need to do two things. One, you need to show that it can generate all of the single qubit gates, and two, you need to have a two qubit interaction gate. So I'm going to do the first one now, which is to show that it can produce all of the single qubit gate operations that you need. So to start off with, I've listed here a couple examples of single qubit operations, your X, Z, and Y Pauli operators, and your Hadamard gate, and there is a whole host of them. Essentially, what you need is a gate operation that takes you around all of the states in the block sphere. And for our Hamiltonian, for a single qubit, we know that the Hamiltonian generates an SU2 group, and so we already know that it's going to be able to achieve this. But let's just be a bit more specific. So what I want to do is consider the case when the system is detuned. In other words, the qubit is detuned from the. I'm consider the case when the qubit is tuned to the battery. In other words, the delta, which is detuned, is equal to 0. And in this situation, the unity operator looks like this. And then I want to look at the case where the system is detuned from the system when the qubit is away from the resonant frequency of the battery, in which case the unity operator looks like this. So now if I want to implement, for example, an X gate, I will put the system so that the battery is tuned with the qubit, and then I'll let the system evolve to time tx, where tx is equal to pi on 2g square root of n, where g is the coupling constant between the qubit and the battery, and little n is the number of photons inside the battery. And when you do that, you get the X Hamiltonian over here. Now, if I want to implement a Z operator, then I set the system to be, the qubit to be detuned from the battery, and let the system evolve for time tz. All right, I'm going to give up. Time tz, and where tz is equal to pi on delta, and delta is the tuning between the qubit and the battery. And if I want to implement a Y gate, then it's simply first doing an X, then a Z. And then a Hadamard gate, you do a Z, X, and Z. And you can do this for all possible single qubit gate operations. The next thing we need to do is to demonstrate a two qubit entangling operation. So the one I've chosen here is an I-swap gate. And what an I-swap gate does is that it flips the 0 to the 1 and 1 to the 0. And to show that our system can implement this two qubit entangling operator, work in the regime of large detuning, where the qubits are detuned from the battery. And then we look at time, let the system evolve to time t equals pi on delta over 2g squared. And when delta squared on g squared mod 4 is equal to 3 and nb is even, then this matrix here will reduce to the I-swap gate. So we have all single qubit gate operators as well as a two qubit entangling gate, which gives us a universal gate set. All right. Okay, so now I want to use our system to demonstrate a couple of quantum circuit examples. This example is to demonstrate a multi-qubit parity probing operation. So essentially we have 3 qubits here. The bottom qubit here is ancillary qubit to probe the 2. And by measuring the bottom qubit, you can determine whether the 2 qubits are even or odd. Even is when there are an even number of 1 states, and odds when there is an odd number of 1 states. Right, and this is the circuit that implements this parity probing operation. And to implement this, what we do is we do an optimization algorithm where we know the target unitary. So we know all of these gate operators, and we know the unitary that we need to achieve. And we need to optimize it with a number of parameters that we can vary or we can tune. The parameters that we want to tune is the frequency of the qubits. These are your omega Q0, Q1, Q1, and also the frequency of the battery. And the other parameter that we want to tune is the time that these frequencies occur for. And so you run it through your algorithm, and then you get a solution. And this is the solution that you get. And this here implements this circuit on our algorithm. Oh, by the way, so all this work is published, and we've also provided the code for this on GitHub if you want to play around with this. Another example is here I'm demonstrating is to show how it can implement a Toffoli gate. So a Toffoli gate, in this case, is 3-qubit gate, and it flips this third or target qubit when these 2 other qubits are 1. So the way that quantum computers work at the moment is that you have your program, and then when you compile it, it breaks it down into its native gate set, which is a set of single qubit gate operations and two qubit entangling operations. So this Toffoli gate circuit here is broken down into this native gate set here. And what we've done, again, is we know what this unitary is. We did an optimization problem to get the frequencies and the timing of these frequencies to implement these native gate sets. And to get this system, this circuit to run, it took about a bit over eight arbitrary units. It's in terms of pi and g. But with our system, we can throw this idea of universal gate sets out the window. We don't need it anymore, because we have effective OR-to-OR connectivity. So instead of having to break it down into your basic universal gate set, we can essentially do it all in one hit, because we know what this total unitary matrix needs to be. We just run the operation on that total unitary matrix instead of breaking it down. And when you do that, you get this as a solution, and the time it takes to run is about half of what it takes if you break it down into its universal, into its native gate set. So that's another advantage of the architecture that we're using. Okay. All right, so now let me talk about the energy efficiency. Okay, so I think we're on good time. All right, so I've got 2 more slides left. The energy efficiency. So what we've already did here in this top plot is to calculate the energy, the amount of heat generated for 1,000 qubit in the, I believe we used the Google quantum computing here as an example. And that's this circular pie chart. We have also superimposed here this circle, this black circle, which is the amount of heat that can be extracted by a fridge. And because for this system here, the amount of heat generated by 1,000 qubit exceeds the number, so exceeds the heat that can be extracted from the fridge, this is a bottleneck. And this means that we can only have 658 qubits in your Google quantum computer. You can improve this by replacing the external cables with superconducting cables, which many companies are doing now. But this, again, shifts the the heat map down a little bit lower, but still for 1,000 qubits, we can't get all the heat out. And so we get about 808 qubits. With our system and with conventional cables, this is its heat map here. Because essentially we've moved all the drive lines. And we can fit in 1,000 qubits, because the heat generator in our system for 1,000 qubits is less than the amount of heat that a fridge can extract out. And so we can get to about 1,400 qubits using conventional cables. If we replace the cables with superconducting ones, then this reduces it further, and we can scale the number of qubits up to almost 6,000. This bottom right-hand chart here shows the amount of energy per qubit that is consumed in a standard conventional superconducting quantum computer. I think we use the Google one again. And the more computations you do, the more energy is consumed. In our system, which is in yellow, the amount of energy consumed per qubit is almost flat for the reasons that I mentioned earlier. There's a slight gradient because we need to read out the computation, and this will always consume energy, and it's unavoidable. But overall, we're going to have a lot of energy saving using this new architecture. All right, so this, I believe, takes me to the last slide. Actually, yeah, this is the last slide. Well, there's one more slide, but this is the last slide that I'm going to talk to. So what I want to talk about here, or just mention here, are some of the questions and challenges in our work. So the paper that was published was a theoretical paper. So what we need to do now is to prove these concepts in the lab. And so we're actually building the circuit now to demonstrate these properties. There are other things that we also need to do, and this is sort of an open challenge for you to, if you're interested, to try and solve, and also work with me if you're interested to try and solve. So those algorithms that we develop, as I mentioned, were solved using like an optimization algorithm, but by no means was that those series of pulses the most optimal solution. So we need better optimizations to get even better efficiencies and quicker algorithms, but there's a lot of room there to improve. Another thing which we're also working on right now is to exploit this OR-to-OR connectivity to develop new algorithms. So for example, flipping the 0 to 1 state, which saw super extensive increases or sub-extent increases in the time it took to flip. That's an example of this OR-to-OR connectivity, which is related to the exploitation of the super extended speed up for new algorithms. So with this new architecture, looking at new algorithms to exploit. So this is a summary page, and I'll end there. I'll just mention that this is the paper, and also you want to reach out, there's my email. Thanks.
Okay, thanks a lot. Do we have questions? Yes, a lot.
I'll start then. Thanks, James, up here.
Oh, I'm really excited.
Very nice talk. Thanks, very nice results. I'm curious about, I've maybe two questions. One is, have you thought about quantum error correction in this paradigm?
We haven't done an explicit error correction circuit, for example, but the parity probing algorithm, that's a basis of many quantum error correction algorithms. And in fact, we're actually looking at quantum error correction now for this system, yeah. But we haven't, for this paper, we didn't do that. Yeah.
Then I'll ask a second question as well, which is, how hard is it, so you say because you can get this entire for the 3-qubit example, for instance, you can directly access SU8 in that case. Yep. How hard is it to compute the pulse sequence for that?
Oh,
it seems that if you could do this well, then you could actually just do the computation itself classically.
Yeah. This is the key. So That one was surprisingly easy, but we wanted to go further. What we wanted to show was that as you have more qubits, you get a super extensive scaling in the circuits. That becomes hard. And then we tried machine learning algorithm, and that didn't help. So that's why this page here is a call for people to come and, point two, to come and help me solve these things, because I think it's a brave new world there. This is like an optimization problem, and I think it has a very interesting maths and physics connotations. Yeah, so again, the codes for the problems I've already solved are on the GitHub, or you want to start, you can start there. But one of the things is that we've done this for something we haven't published yet. We want to show analytically that the algorithm, that the solution we have is a global minimum. For some things we can do, or one thing we found we could do. So the solution I found there is I think it's a global minimum there. I think there's even better solutions out there, but yeah, it's an open question that we need to solve. Yeah.
Right. I have two questions too. Is that okay? Or yeah. So first, I feel like what you're doing is substituting only the wires that are like are sending gate pulses to the qubits, right?
Yep.
So at the start of the presentation, you said that initially you have like 2.5 wires per qubit. So substituting these wires by the battery that itself should have like wires.
Yeah.
Say. So what is the ratio of wire per qubit?
Yeah. So okay. So there's about 2.5 wires per qubit. The one that all have is a drive line and a flux line. So we want to remove the drive line. So if we have one qubit for say 1 battery for 10 qubits, we can remove 10 drive lines with one line for the battery, but we still keep the flux line. So this is sort of graphically represented in this heat map here. What we've done is removed all of the green, but we've kept the flux line. So that's sort of gives you an idea of the amount of cables that we could remove. So roughly by half, I think. Yeah.
Okay, thanks. Yeah. And this brings me to my next question, which is, let's say we have 10 qubits connected to the same battery.
Yep.
Does that mean like the qubits are also all connected?
Yes.
Okay.
Effectively, all
cool.
correct.
Okay, thank you so much.
Yep.
So it's me. Sorry. Okay. So first, very interesting results. So you showed that the fidelity of in the first part, the fidelity of the operation increase when the number of quanta per qubits increase, which is somehow, I would say, expected. And so if you look at the opposites, so when there's few quanta per qubits, it means that your operation is not unitary. So it's increasingly non-unitary. And so did you look at that in the optic to, for instance, reinitialize or increase the purity of your qubits?
Yeah, I think I answered your question, but so the right-hand side here, so it is unitary if you include the battery inside your system. So the reason that you don't get, if you get these errors is because you take the battery out, and these systems are entangled with the battery. But the amazing thing is that as you increase the number of qubits, even though there's more entanglements, more complicated, the error actually reduces. You get closer to the one state.
Yeah, but so it's unitary, but from the point of view of the qubits, it's not unitary.
Correct.
And so when you want to do like a computation, unitary operation, it's a bad thing, but you can look at it also as an opportunity, because you have a possibility to do non-unitary operation, which means that you can, for instance, be able to reduce the entropy of your qubits. So I'm asking whether you.
Yeah,
looked
no,
at
I like it. I
for
like it.
purification or thing
I like
that.
it, yeah. I think, yeah, your idea, no, we look at this, your perspective is, let's lead into, from one perspective, from the qubits, excluding the battery, it is non-unitary, and let's lean into that and see if we come up with cool non-unitary algorithms, yeah. No, it's not something we looked at, but
Okay, okay.
certainly,
Okay,
if you have some good ideas, yeah, please reach out, yeah.
Okay, thanks, James, again.
Yeah, thanks.